Recording in progress.
All right. Don't know if you guys can hear me. Let me know if you can. Okay, perfect. Sorry, I need to mute my audio on the other end. Disconnect myself from. There we go. All right. Um, there's only about like 17 people here. Do you guys want to wait until like five past to start, or do you guys want to just like get right into it? Or should we just say screw it? The people who get here late will like just have to suffer or something. Yeah. So welcome to my MATA37 winter review seminar for the final exam. Um, I've held a few review seminars in the past, so from the summer semester as well as the previous winter semester, and I have posted those recordings on YouTube. So you could probably find them just by searching MATA37 review seminar. They should show up. But one thing to keep in mind though is that the summer semester one was not taught by Kathleen, so it would have different content coverage versus what Kathleen would probably cover. Um, for the most part, I'm going to be going over questions that I've kind of curated that seem very Kathleen-like in terms of what she might ask for, what things that I've seen her ask in the past to kind of better help you guys understand what the scope of the final exam is going to be. And well, just keep in mind that she can ask you for complete and accurate definitions of mathematical objects that you guys have defined in class. So these would be things like, hi Billy, these would be things like the interval of convergence or define uh, what it means for a series to converge, define the Darboux definition of the definite integral, things like that. You want to be able to completely and accurately, so very precisely define these things. So study those. But I'm not going to be covering any of those during this final or this review seminar. And just a heads up, this review seminar is going to be recorded. I still need to get word from Kathleen if I can post this or like post the link, make it public. But if not, then I'll just have to send out the notes from it. Okay, well, let's get started. So as per normal, Kathleen usually starts with a true and false section. So in this section, it says for each of the following statements, indicate whether it is true or false. Justification is not required. And usually this is how things go. Kathleen will never really ask you for justification for true and false. There's a question, will there be proof of those theorems in the exam? What theorems in particular? Would it be any theorems in that was covered in class? I highly doubt that Kathleen would ask you to regurgitate a proof that was already done in class. So if something was proved in lecture, such as like BMCT, it was proved in lecture, she would not ask you to reprove it. That's just memorization and regurgitation, and that's not something that we want to test in A37, or at least Kathleen. It would always be new proofs of things that you can just prove using the things that you define in class. Yeah, so there won't be proof of any of those theorems on the final. Okay, but why don't we get started? So just if you think it's true, type T in the chat. If you think it's false, type F in the chat. Or if you want to unmute yourself, ask a question, please do so. Okay, question 1A. If F has a horizontal asymptote at y equals 0 and F is positive, continuous, and decreasing on 1 to infinity, then the area of F against the x-axis on 0 to 100 must be finite. What do we think? Do you think it's true or false? Okay, we have one false. Anyone else? False. Okay. Okay, a few more falses. Anyone think it's true? Okay, maybe people are too shy to put their opinion in chat. Well, the answer is false. This is in fact false. But for those of you who did say false, is there maybe a reason that made you think it was false? This one is false. I'll circle that. What kind of told you that this is false? Is there a specific example of a function that you can define that satisfies these properties and has infinite area? Yeah, 1 over x. F of x is equal to 1 over x is our classic example of a divergent integral. Um, this integral will always diverge whenever it includes any part of 0 to infinity or 0 to something. It'll always diverge. So that being finite would be the false part. So something like this diverges, which means that it has infinity or negative infinity as its evaluation, which means not finite. So any function with a vertical asymptote x equals 0, yes. Any function that has a vertical asymptote, well, actually, probably not like 1 over x squared. That one I believe will converge. Wait, actually, no, that one diverges as well. Yeah. So I think pretty much any function that has a vertical asymptote at x equals 0 should work. But all we're looking for here is one example of a function that this is not the case, and that would suffice. Okay, cool. Now question B. Consider the sequence defined by an is equal to arctan of n minus cos of n pi plus 1 over n plus 3, root 3 of minus 1 minus n, 1 over n. Since the limit of this equals to some number, pi over 2 plus 1 over, or root 3, we have that an diverges. What do we think? Okay, we have some falses. Okay, we have some confident falses and we have some people kind of unsure. But this is a very common thing that I see a lot of students mess up. It's the discrepancy or like the difference between the theorems that we can use for series versus the ones that we use for sequences. Notice that this guy, he's a sequence, not a series. We can only use this div test kind of thing, this limit, to say something that diverges for a series. However, this is a sequence. So this only applies to series. If this said something like this diverges, could we say that? Yes, 100%. But that's not the question, right? So, false. Perfect. I'm glad you guys at least understand that. All right. C. This one's a hard question. This is gonna involve a lot of the stuff that is like from later in the course. So, power series. So I would highly recommend you brush up on your power series definitions. Okay, suppose that this is a power series. A Maclaurin series, I don't know if you guys have covered what that is. Have you guys covered what a Maclaurin series is? Yep. And does everyone understand what it is, or do we want like a little recap? Yeah, of course. A Maclaurin series is just um a Taylor series that is evaluated at 0. Or centered, or not evaluated, sorry, centered at 0. So remember, do you guys remember what your Taylor series is? Your Taylor series basically is just an approximation, right? If you have any function, you can always approximate what that function is using a polynomial. That polynomial will give you a really good approximation, right? If it's an infinite series or or if it's an infinite sum. So the Taylor series is defined as follows. So in this case, A is the center. Um, F to the power, or this quote unquote power of n, this is just the nth derivative of f. And we take the nth derivative of f, evaluate it at our center A. Note that this is going to be well defined for, well, if you have a function that has a Taylor approximation or Taylor series, because n equals 0 won't give you a zero denominator, right? It's going to be well defined. So this is just our general definition of what a Taylor series is, right? It's just an approximation or a function that can be approximated by a series, or that will be exactly written as a polynomial series. Okay, but a Maclaurin series is one with the center of A, so that means that we can write it like this. This is what our Maclaurin series is. Okay, and I'm realizing now that I probably didn't leave enough room. So I'm gonna like shrink all this stuff down a little bit. Okay, hopefully that was a good like little recap refresher. Does that kind of make sense? Okay, but to the actual question, it says that this is a Maclaurin series that converges at x equals 5. Okay, it diverges at x is equal to -7. Then the series of this guy converges. Okay, so the approach with these kinds of questions is to always try to figure out what your radius of convergence is, right? Your radius of convergence is this distance away from your center A, such that when your x values are evaluated, or when your x values are within this interval, your series will converge. So something like this, right? Where R is your radius of convergence, A is your center. Notice in this case, because we have a Maclaurin series, our center is 0. So that means that it's just going to be minus R and R. We want to be able to tell what our radius of convergence is. So remember, um, there's if there's any point of convergence, or if there's convergence at any x value, then that means that the radius of convergence has to cover it. So that means that if it converges at 5, then that means that our radius has to be at least, at least 5. Right? So we can say this. We can say that our interval of convergence looks something like this, at the very least. We can't say anything about -5 though. We're not allowed to say that, hey, our series converges at -5, because we would have to check what it evaluates to see if it actually converges at the endpoint. Okay, but we do know that it converges when x is evaluated at 5, so we can claim that it converges here. We can include it in our interval. Okay, this diverges at -7. That kind of checks out because in our interval of convergence, -7 is not in here. So notice -7 is not in here. Okay? So now we just need to figure out in this, or from that series, what X value was put in there. What was that evaluated at? Any ideas? Okay, it seems like a few of you are getting it. Yeah, it's -4, right? Because our Maclaurin series looks like this, right? Or our power series in particular, it looks like this, right? This thing to the power of n, it looks a lot like this guy, right? So our x value is -4 in this case. So x is equal to -4. So what do we think? Do we think that this is true or false? Exactly. Just do a little bit of analysis. This is true. This will converge. This -4 is within this interval of convergence, so it must converge. Beautiful. This kind of question is really common for Kathleen to kind of put on there, whether it's a true or false, whether it's a here's the radius of convergence, which one of these values will cause this series to converge, things like that. Kathleen loves these because it's creative and it's fun. So be very comfortable with these kinds of questions. Okay? The next one, let f of x be greater than or equal to 0, be Riemann integrable on the closed interval AB. If the interval of f of x from a to b is equal to 0, then f of x must be equal to 0 in AB. Is this true or false? This one's a tricky one. Sometimes it helps to draw a little picture of what this looks like. Okay, we have a few answers here. Some people are saying true, some people are saying false. Okay, a good amount of you are saying false. You're correct. This is false. Why is this false? Is it possible to have an integral? It can pass 0? Mm, not really the reason I was looking for. It can pass 0, you're right. Um, Discontinuities. Well, we know that it's Riemann integrable, so that means that there's going to be a finite number of them. The area can be canceled out. Not necessarily, because in this case, f of x is greater than or equal to 0, right? Gervier got it. Yeah, when A and B are equivalent, when these guys are the same thing, take a look at when those two are equal. Whenever you have oh, sorry, that was spoilers. Whenever you have a interval where A and B are the same, so consider when A is equal to B, I can have any function I want, any positive function I want, right? But if A and B are equal to each other, then that means that I'm only taking the area of this one line, right? It's gonna be non-zero here. Oh, whoops. It's non-zero in this case, right? And the whole function it's whatever it wants to be. But when these two values are the same, you're only finding the area of a single line, and that we know is always 0. So, despite what this function is, it's not guaranteed to be this. Not guaranteed to be 0. If I had put the condition that A is less than B, strict inequality, A is less than B, then this would be true. So very, very minor edge case, but it's really important to think about these. Okay? To those of you who got it, congrats. These are challenging questions. By no means are any of these easy. All right, but next one. If the series of AN converges, then AN is decreasing. Why isn't discontinuities a possible answer? But yeah, finite discontinuities also work. Um, but you can't have so if you have finite discontinuities over, so let's just say you have something like this. So let's just say that this is A, this is B. You're saying you want finite discontinuities, so like something like this. Let's just say you have that. You would need an infinite number of jump discontinuities for this to not be possible, for the thing to be zero. Because each one of these sections will evaluate to something, right? You still have area here. This is still area, right? And none of it's going to cancel out because it's positive, right? F of x is positive. So that means that you'd still have area, but the function's not equal to zero. 1 point positive. Okay. I should have been a little bit more specific in this question. Um, for all x on AB. Is this still Riemann integrable? This is Riemann integrable. If it's zero, yeah, that would also be Riemann integrable because that would be a finite number of jump discontinuities, right? If it's zero literally everywhere else, so this is your function, but like let's say at B, it's a point, right? This is still Riemann integrable. But yeah, you guys are right. I should have clarified. This should have been a condition for this question. Yeah. Okay, I like this. You guys are like thinking about a lot of edge cases here. This is good. All right. But this next question, if a series of AN converges, then AN is decreasing. What do we think? Okay, overwhelming false here. Anyone else think this is true? Anyone think this is true? Okay, but for those of you who said false, you guys are right. But can you think of a counterexample? So a convergent series that isn't decreasing. Yeah, that's a good example. Um, so these are so I want you guys to be very aware that whenever you're thinking about counterexamples, it's always usually going to be the same set of series or sequences. There are very classic examples of things that we take to be counterexamples. So, for example, the alternating harmonic. That's a very good example of something that's a counterexample for something. The harmonic series, very good classic example of something that diverges. 1 over n squared. That's a good example of something that converges. So you want to always have these things at the top of your head when it comes to these counterexample kind of questions. If it's increasing and bounded from above, um, if it's increasing and bounded from above, that would be for BMCT, which is only applicable for sequences. So BMCT is different from this. BMCT doesn't give us that the series converges. So I'll put that as a little note. an going to zero doesn't mean that it's decreasing yet. Oh, were you saying that that's an example of where it could? Yeah, yeah, yeah. That would be fine. So something like this, right? Something like this would probably series would pr probably converge, but sequence or and yeah, but sequence is increasing. So let me be correct about this. We're taking all these values and we're summing them up. Yeah. Okay. I didn't know if that was misunderstanding there. Okay, cool. I'm glad that you guys are like picking up on these, getting a little bit better. These are tricky examples or tricky questions. All right, question F. Every function has more than one antiderivative. Is this true or false? Damn. So many of you guys answered for this question. This is a super simple question, but it's actually false. Yep, Eileen got it. It's false. Why is it false? Because at face value, this seems like it's very true. This seems like exactly. What if it doesn't have an antiderivative? What if it's not integrable? If your function's not integrable, it doesn't have an antiderivative, there aren't more than one. In fact, there's zero. What condition could I add here to make it true? What do we call that? If it has one? What do we call, or what's our little condition to make sure our functions are integrable? Continuity. Continuity here would make this true. Remember, continuity implies integrability? So if it is continuous, we could say every continuous function has more than one antiderivative, or every integrable function has more than one antiderivative. You could do either or. We just need the condition that it is in fact integrable. Okay. See, that's a question that I feel like a lot of students would miss. And sure enough, a lot of you did. But now you know. Make sure you are very, very keen on checking everything. If it looks like a very simple question, chances are it's not. Read into it a little bit. Okay. Next question. Let A and B be real numbers where A is strictly less than B. Yeah. You're welcome, Leoli. Suppose F is bounded on AB. If there exists a partition P of AB with UFP is equal to -2 and LFP is equal to -3, then F must be integrable on AB. Okay, well, we all know what this is kind of hinting towards, right? It involves UFPs, it involves LFPs. What is being tested on here? Darboux. Does anyone remember our Darboux definition of the definite integral? This should be on like your fingertips right here. Exactly. So it's your so you can either yeah, you can either use this or you can use your epsilon reformulation of it. I prefer the epsilon reformulation because it does involve this like this universal quantifier. So having a statement that's quantified usually means use your epsilon delta statement for it. So for all epsilon greater than 0, there exists a partition P of AB such that UFP minus LFP is less than epsilon, right? This is our epsilon reformulation. So let's test this. We know that there exists, so let's suppose epsilon is arbitrary. We know there exists a partition of AB. We know what the UFP and LFPs are, right? The UFP for this partition is equal to -2. The LFP is equal to -3. Let's subtract them. What do we end up getting? We end up getting 1. Is does this is this gonna be less than every single epsilon that we choose? You're right. No, it's not. So there exists some epsilon that we can choose to make the statement fail. So epsilon equals to exactly 0.5 would fail this, would make this fail, which means it's false. So when you're doing these kinds of questions, it's very helpful to write out what the statement is that you're working with, right? To actually give you some intuition. Okay, next question. Suppose G is at least thrice differentiable on R. Thrice just means 3 times. If G of 0 is equal to 6, then G prime of 6 is equal to the integral of G double prime of X from 0 to 6 plus 6. What are we thinking? Do we think this is true or false? Oh, no one's answering. My internet didn't die, right? Okay, so we have 1 false. Anyone else? Another false. Okay. Come on, be confident in your answers. And make sure you use all the information that's given. Okay, for those of you who said false, you're right. It is false. So take a look. This is just a rewriting of FTOC 1. Right? We know that this integral, 0 to 6 of G double prime of X dx, this is going to evaluate to G prime of 6 minus G prime of 0. Right? But we know that this is, we don't have any information about this. So it's because I didn't put a prime right here. If I said prime, then it would be true. So if I said this, then it would be true. If G prime equal to 6, then true. Right? I would be able to rearrange this. So suppose I did say G prime was equal to 6. I'd be able to rearrange it and move it to this side. Does that make sense? Are there any questions about this one? Makes sense? Okay, cool. Sorry, I should probably write that this was false unless green added. All right. Last true and false question, and then we'll get into like the longer answer questions. Let f and g be not integrable on CD. Then any linear combination of f and g must be not integrable on CD. And do you guys all know what a linear combination of something is? You guys have all taken, well, finished your exam for A22, I hope. Okay, so a lot of falses. Okay, yeah, this is false. But why? Whenever you think of a true or false question, you always want to think about the why behind it, even though it's not necessarily rewarded. You want to be concrete in your answer. Exactly. If you take f and g to be the same, right? Or f is equal to minus g, then we get that f minus g is equal to 0. This is integrable. And this is a linear combination. Exactly. Really simple, super clean answer on this one. And that's kind of, so my general tip for true and false questions is don't change your answer or don't go against your gut unless you have a reason to believe that you're wrong, unless you have a concrete reason to believe that you're wrong. So with all these questions, you guys were able to come up with counterexamples or reasons or intuition that told you that they were true or false. Carry that with you as you actually take the final exam. You have to have a reason for your answer. If you're unsure, you can guess by all means, but when you're actually like confident in an answer, it should be because you have mathematical reasoning behind it. Okay, so that was all my true and false. How do you guys feel? Okay, we got a thumbs up. A lot of thumbs up. Whoa, okay, great. So let's move on. Let's make quick work of this. So now moving on to short answer or shorter answer. Answer the following questions. Make sure to justify your solution completely. Determine the Maclaurin series for the following function. So this is just testing, can you use the definition of a Taylor series and find what the Taylor series expansion for a function is. So remember, we know that any function can be rewritten as a Taylor series. So something like this. So f of x is equal to this. Same thing as that, evaluate at 0. Notice, again, I just omitted the x minus a to the n, right? Because we know that a Maclaurin series is centered at 0. So we don't even need to worry about a, because it's just 0. Cool. So now we just need to find a pattern in what the nth derivative looks like. So we need to find a way to rewrite this guy. So let's take the derivative of our function. So this is the reason I use 2 to the x in this example is because a lot of students were very iffy on their derivative of exponentials when I was marking the midterm exam. So be very confident in your differentiation. The first derivative of 2 to the x is 2 to the x times ln of 2. When you evaluate at 0, so x equals 0 will give you f prime at 0 is equal to ln 2. Cool. Let's try the second derivative. We get 2 to the x times this ln of 2 stays the same, right? But then you have another ln of 2. So I'm sure you guys are already sensing the pattern. We already kind of see that it's just going to be ln of 2 to the power of n. So that means that we can rewrite this as follows. This would be what the Maclaurin series would look like. And this is also a very Googleizable thing. That really funny word. You can kind of Google what the Maclaurin series or the Taylor series expansion is for any function. So I would highly suggest you figure out or try to like practice this and then confirm your answers on the internet. Okay. Next question. Any questions on this? If there's no questions, I'm going to move on. Okay, next one is give an example of two convergent series, uh, an and bn, such that an times bn diverges. So prove that your example satisfies the criteria. So we need to give examples of an and bn. You can use quintessential examples of convergent series, but we want one that diverges when you multiply the two general terms together. So what would we get? I like that idea. We already know that, like, I would usually start backwards with these kind of questions. We want to find a divergent series. Okay, so I'm just going to use 1 over n, our harmonic series. So, like, that's a decent idea. I like where you're headed. But I always start with this because I know what the output is going to be, right? We start with what we want. We want something this, like this. So let's see if there's a way that we can recreate this. I like the two alternating harmonic example, but is there a way that we can modify it? So you said that the denominator would be it would turn to an n squared, which converges. Okay, well, is there something that we can do to modify it? Yeah, we can put a square root over it. Can we confirm that these converge? And if so, how? How can you prove it? Yeah, by AST, right? We need to find what our Bn is. We need to have an alternating part, and we need to show a few things about Bn, right? So Bn is going to be this thing, right? And if we show it for one, then we've shown it for both. So Bn is equal to 1 over root n. Can we confirm that this goes to 0 as n goes to infinity? It does. Lovely. Can we confirm that this is decreasing? Yes, it's decreasing. What else do we need to show? We need to show that it's always positive. Can we confirm this is always positive? Well, it is because our numerator is positive, right? 1 is positive. And there's no way for a denominator um that's a square root to be negative. So we have positive on both, so that means that the entire thing is positive. So we have this condition is satisfied. So convergent by AST. Yes, the session will be recorded. I will get back to you, well, not get back to you, but you'll see later if I was able to um post the recording, then I was allowed. But if not, I'll just put the notes on Piazza or something. Good luck on your exam. So yeah, these two converge by AST, and we get this, our harmonic series, which we know we can just quote and say that this diverges. Okay, any examples of this? So always try to start with what you want instead. Try to start with what you kind of know. Start with what you want and see if you can reverse engineer something that will give you what you want. Any questions on how we came up with this? Okay, if not, I'll move on. Okay, next question. This was one that was on a previous final exam. So this is very viable. So it says find all values of the constant b in the real numbers, the positive real numbers, for which the following series converges. So we want to somehow analyze this to make it converge. Is there a way that we can do that? Do you have any ideas? Hmm, absolute value of n is less than 1. I would, mm, well, we're assuming that everything here is well defined. Um, but also we know that n is, it starts at 1. So yeah. Can we use p-series here? I like that idea. Ln in particular, ln and exponentials are always things that we can always rewrite. We can always shift these values around to make them convenient for what we're looking for. In this case, exponentials can become denominators, right? So if there's a way for this to look like a 1 over n to the p, that would tell us a lot. We can use p-series. But is there a way that we can rewrite this to having the n on the denominator and then to the power of something? I think we can. Let's start with what we know. Let's start with trying to rewrite our general term. So a common trick whenever you're dealing with exponentials is to always take things to the power of e and then take the ln of the original base. So something like this. Right? This is by algebra. We can always do a move like this, right? Because e and ln are inverses of each other. Okay? But now let's use our exponent laws and multiply the powers. And what do we know? The fact that multiplication is commutative, right? Multiplication commutes. So we can switch them around. Oh, but these things cancel again. They cancel. So what are we left with? We're left with n to the power of ln b. Okay, so now we've written this thing with a base of n. That's awesome. This is good. This is what we want. But we don't just want a base of n. We want that n to be in the denominator. So is there a way that we can push this base to the denominator? Exactly. We can introduce a negative in the power, right? After we push it to the denominator. And this undoes that negative power, right? Okay, so now we can analyze this as if it were a p-series. So consider this. What do we need to know about ln of b or negative ln of b? What should negative ln of b be? Well, this is our P. What do we want for this? Well, we want ln of negative ln of B to be greater than 1, right? So let's do some algebra to see what value of B can be isolated from this. So let's just rearrange. So doing the same thing, you can multiply both sides by a negative. So ln of B swaps the direction of the inequality. Then we can take things to the power of E, right? Or to the base of E, because E is increasing, which means it maintains the order of the inequality, right? So E to the X is increasing. So it preserves the inequality, right? Remember our justification? We kind of need this. Then the E and the ln cancel out, and we get that B is less than 1 over E. Okay, so we found a upper bound for B, but we want to find all the values of B. Is it just the ones that are less than E? What if B was negative? Would it work? No. Why wouldn't it work here? Because at some point we're putting B inside ln, which means that it has to be positive, right? And even in the question, it says find all constants B in the positive real numbers, right? So that just means that B is positive already, right? So that means that our final answer should look like this. Does this make sense to everyone? I know, very algebraically intensive, very unintuitive to think about even doing, but I wanted to do a question like this because it makes it seem like, or it puts it at the forefront of your mind. So if you see something like this on the final exam, this kind of algebraic step is always available to you. Does anyone have any questions? Speak now or forever hold your peace. Okay, I'm moving on. So this question, it's what I consider to be free marks because all it is just proving an inequality. So it's prove that the integrals satisfy this inequality, but what inequality are we trying to prove? What is the tool that we're going to use here? Any ideas? Is there maybe like a property that we learned about integration that we can leverage here? Something? I know it's hard to type out the math in chat. Exactly. We just need to prove that f of x is less than or equal to g of x, and these things are both positive. Because if we have this and we have that they're both integrable, then we'll on well the interval that we're interested in, then we'll have that their integrals can be taken, respects inequalities. Right? I know this is like very early on in the course, but it's also something to keep in mind, right? this is not just a final exam that covers majority, well, it covers majority later content, but it can also cover stuff from before, even the small things that weren't tested on before. Um, do we want to all go through this together, proving these things, or do we think we got it? So the recording is not necessarily guaranteed to be posted. I have to ask Kathleen if I can post it. But the notes will probably be able to be posted and they will be on Piazza. Okay, so this is gonna be left as an exercise. And I would suggest starting with this fact. Um, hmm, yeah. Oh, they got removed. Oh, okay then. Unfortunately, I can't guarantee that this is gonna get uh well, the notes will be posted. So make sure you take good notes. Okay. But now that was like all the short answer kind of stuff. Okay. So now it's finally onto like the bulk of this course. It's all the series and integration. So for a lot of these, it's gonna be very heavy, but I wanted to go through like a series and integral checklist just to recap all the things that or all the tests that you have at your disposal. Okay? Um, Also, quick question. Do you guys want a break? We've already been doing math for like about an hour. Do you guys want a break or do you guys want to just like keep pushing through? You guys want a break? No break. Keep going. Okay. I'm gonna need more of a consensus. Break. A lot of people saying break. Some people saying push through. Okay. I'll create a poll. It'll be break, no break, break question mark. Did you guys get prompted for quick break? Okay, there we go. Oh. I'm watching these things like happen real time. So I see like the fluctuation. Okay, all of you have answered. The verdict is taking a break. So we'll take a 5-minute break-ish. So we'll be back at 2:05 officially, okay? Go stretch your legs, grab some water, and then maybe go to the bathroom, come back, and we'll continue some math. Okay, it is now 2:05. I hope you enjoyed your very quick 5-minute break. Shall we get on to some more math? Just give me like a little thumbs up in chat or a little thumbs up if you're back and you're ready. I just want to see like an overwhelming like influx of thumbs ups. So we have like 3 people back. Oh wait, maybe like a couple more seconds. Okay. People seem to be back more or less. Okay. So let's get back to business. And keep in mind, I am willing to stay like 30-ish minutes past 3 o'clock in case you have like a bunch of questions afterwards. Okay, but without further ado, let's go through our series checklist. So again, whenever you're thinking about series or determining whether series converge or diverge, you always want to have a checklist in order from easiest to identify and fastest to execute to hardest to actually use. So I like to think of it in this order from top to bottom, starting with div test. Always, always, always check div test. Whether you think it converges or not, check it. It's always, always, always a good thing to check because you never know when you're going to miss it. GS test. That's your next thing. It's always going to be your sign to use GS test is when you have something to a power of n, when you can see a very, very clear ratio of sorts. Your P series test, obviously, when you have a 1 over n to the power of some p, super easy to identify. Your ratio test. A lot of people don't like ratio test. I love it. It's super formulaic, it's super easy to use, and it's really useful when you have factorials or really, really, really odd powers. When you have weird powers of something, use ratio test. CT is when you have a boundable function that's in your general term. So things like arctan, things like sine and cos, things like I'm trying to think like even just like constants, right? That you can bound from above, bound from below, things like that. Um, you want to use IT when something looks integrable. It looks like if you just change the variables from n's to x's, you get something that you can integrate really easily. So these would be things like 1 over x's in conjunction to lawns appearing somewhere. If you have an arctan somewhere, but then you also have a 1 over x, 1 over x squared plus 1 somewhere. That would be a good thing to check. AST, if you have an oscillating part, and by definition is your very last resort thing, but it usually happens when you have a something that's being added and then something is being subtracted to it. And these are going to be telescoping. One is going to cancel out the other if you expand the sum in total. An honorable mention that I feel like a lot of people forget, and I definitely did forget when I first took the 837 final exam. Absolute convergence implies convergence. So if you feel like, hey, the negative version of this sequence or the series is really troublesome and hard to deal with, consider this absolute value of it. That might be a good way to make it easier to determine convergence or divergence. Just keep in mind, if it doesn't absolutely converge, doesn't mean that it doesn't converge. So you still, if absolute convergence doesn't work, you still got to determine convergence of it. Okay. Um, so that's your series checklist. Your integral checklist is, well, U sub, first of all. Then it's int by parts, PFD, geometric properties, and then trig sub. Trig sub is always your last resort. U sub is used when you have a derivative that of some function that appears in the integrand. Int by parts is when you have products of things that don't relate to each other whatsoever. If you have a proper rational function, then that means you could use PFD. A geometric evaluation would be like when you have a polynomial under some square roots. This would be super easy. PFD is your partial fraction decomposition. It's when you're splitting up your fraction, your rational function into smaller pieces. Your properties would be when you're using like the thing of like even and odd functions over a symmetric interval, right? These will evaluate to 2 times the interval of one side or the integral of one side, or just 0 if flat out if it's an odd function. Then trig sub is the hardest to do. It's your last resort. And it's usually if you have a sum or a difference of squares. I know that's a lot of information to take in, but it's really, really critical to have a mental checklist in order that you always check, always go through these. Okay, so let's get started. Series and integration. So this is going to be a combination of series and then integrals. The very first one. Determine whether the following series converge or diverge. Find their sum if possible. So, um, if you're in my tutorial, you've seen this example before, or you've seen probably a few of these examples before, so don't feel bad if you don't want to tune in. Um, but this is something that showed up on my final exam, and I didn't know how to deal with it until later, which was really unfortunate. But what do we think? Do we think this converges or diverges? And if so, using what test? And remember our mental checklist. Okay, Mikkel thinks it diverges. Use div test, use div test. Okay, sure, let's use div test. Obviously, it's always good to check this, right? So the limit of n sine of 1 over n. Okay, but doesn't this how do we know that this diverges? What is this limit? And how do we know? So remember, with div test, you not only need to determine what uh it like what the limit is, you need to be able to say it's non-zero. You can use L'Hopital's rule, yeah, or you can rewrite this limit. I like the idea of rewriting the limit. So I'm actually gonna call theta, for example, 1 over n. I'm just gonna do this. I'm gonna rewrite my limit because this is something that we learned how to do in A31, right? For those of you who are in my A31 tutorial, you already know how to do this. For some of you who are in different tutorials, you might need a little refresher. So here's that for you. As n approaches to infinity, what does theta approach? It approaches 0. Cool, right? Because if this approaches to infinity, then that means that theta goes to 0. Lovely. And I can rewrite this as sine of theta over theta if I just move this n to the denominator like this. So, right? That's an algebraic step I can make. And does anyone remember what this limit equals to? How do you know? This is from A31. If you remember, you had a well, not long, but it was a little list of common limits or very weird limits. This was proved using squeeze theorem, if you remember. So things like your cosine limit, your sine limit, things like that. These are things that Kathleen also wants to test on. She's implicitly also testing you on your A31 knowledge through all of this. Hence, it is a prerequisite. So this does not equal to 0. So by div test, diverges. So this is just something that you should review from A31. I'm not going to get into the details of it because we are under a time constraint and I want to get through all these questions. But if you have any questions, I can like stay back a little bit and kind of explain to you why this works. Okay, this question. So remember, our mental checklist. What do we always check first? Well, we always check div test. Unfortunately, div test fails here. P series. Okay, but this is not a 1 over n to the power of p. GS test? Well, this is not a ratio to the power of n. This is a ratio, quote unquote, to the power of ln of n. Okay, I like that idea. Remember that little trick that we used for this question? Rewriting a base to the power of ln of that thing? We can do the same trick here. rewrite this, shift the variables, shift the values. And in the same way, we can rewrite this to be this. I'm not going to fill in all the gaps because I'm sure that you guys can do it using the knowledge that you now have, but we can swap them like this. Obviously, you'd show all your steps. I'm not going to, but. So now, you guys are saying use p-series test. What is p equal to? You need to convince me that this is a p-series. P is equal to ln of 3. Okay, but we need to compare this to 1. Do any of you know what ln of 3 equals to? I mean, you guys don't have a calculator during a final exam, so how are you going to do this? Yeah, 3 is greater than E, right? E is about 2.72-ish, right? Something like that. Okay, ln is increasing, which means it preserves inequalities, which means that this is true. But what do we know about ln of E? This is just equal to 1. So by transitivity, we get that ln of 3 is greater than 1. So by p-series test, it converges. Again, testing your little A31 knowledge, right? How comfortable you are with these functions, how comfortable you are with manipulating inequalities. This is very key. The trick is not always apparent when you first look at it. Okay, but this is good. Next one. What would you say that these types of questions would be out of? Maybe 3 or 4 marks at most. So these questions, depending on the technique that is required to be used. So for like a p-series question, like this one would probably be out of 4 marks. This one would probably be out of like 3 or 2. Yeah. Just because of, well, what we expect of A37 students. This question might be out of 3. Okay. So someone thinks div test for this question. Does anyone disagree? I mean, I don't know. This kind of looks like an AST kind of thing, right? We have an alternating part right here, right? So why would we use div test? Shouldn't we just like skip over it, not use it? AST fails. Good. So if AST fails, due to BN does not tend to 0, try div test. But again, remember, div test is the first thing that you should use. It's always the first thing. This general term, this AN, it goes to infinity, right? Even if you take L'Hopital's rule of it, right? Like you do an implicit kind of L'Hopital's rule, because we can't use L'Hopital's rule on discrete functions. We can't take limits of quote unquote discrete functions, right? But it gives us some intuition, right? It at least tells us where this limit's going to go. This, in fact, does go to infinity using L'Hopital's rule. I don't know what the notation for it is. Is that? Yeah, so this diverges, goes to infinity, which means diverges by div test. Your final answer should always be like it converges or it diverges by what test? Always. Because us as TAs, when we look at a question that a student has answered, we want to see like what their final answer is. We usually look from bottom to top. So if we see that your final answer is correct, we analyze the rest of it afterwards. It just makes it more efficient. Okay, but what about this? What do we think? CT? Okay. CT could work. I think there's an easier thing though. I want to point your attention to this. Where have you seen that before? I don't know, maybe in some of your tutorials you've seen people rewrite this, or your TAs rewrite this as, well, this is just n pi, which means it's an approximate, or it just does this, right? It's a -1 to the n. It acts similar to that. So we technically have an alternating part here. I'm not saying that CT won't work. CT most definitely will work, but remember where it is on our checklist. CT is a bit lower than AST. I'm gonna check AST first. So remember. So what is our BN? In this case, our BN is 1 over n plus 1 all in the square root. Can we confirm that this goes to 0? It will. Can we confirm that this is decreasing? As n goes to infinity, it is gonna, go downwards. It's not gonna get bigger. So it is decreasing. You would have to show this rigorously using inequalities, but, you know. And remember, we can't use differentiation here to prove that it decreases because this is a discrete function. We can't take derivatives, quote unquote, of discrete functions. We can only do that for continuous functions or functions that have a derivative. Uh, these ones are not one of those. So we have to do this by hand. So we know that this, like, starting with this. All right. And then you would just do what you need to make what you want appear. Okay. What else do we need to check? We need to check that Bn is positive. Can we confirm it's positive? Well, it is. Again, same thing. Our square root in the denominator only spits out positive values. Our 1 in the numerator maintains the positiveness of it. So, positive. But again, you have to show this. Which means converges by AST. Cool? Okay. Last but not least, this is the last of our series questions. What do we think? Can you move up a bit? Yeah, sorry. But we're on question 5 now, so what do we think? What series test could be applied here? Remember, we always want to use div test first. Div test is always our first bet. This tends to 0, so I don't think so. Some people are saying CT. Why not IT here? I mean, I see a ln and a 1 over n something here. Why can't I use IT? We even have that this starts at 3. No, we can, but that's extra work. This is just a very small chain of inequalities. I don't want to have to define f of x or f of n is equal to an for all n, whatever, or f of n is equal to bn for all n, and then say f of x is equal to this, and then differentiate. That's a whole thing. We want to make our series tests as simple as possible. I put IT below AST for a reason. It's because we can always do something like this for AST. Yeah. But for this question, why not use IT? Hmm. But we want a 1 over n or 1 over x dx, not a 1 over x squared dx, right? So you could try IT and then realize it doesn't work. But there's a reason that I put CT above IT. CT is so if IT works, usually CT will work better. It's very, very specific when IT is preferred over CT. But this doesn't look integrable, right? I like yeah, ln n could be my u and then 1 over n, but then that's 1 over n squared, and I don't have a 1 over x squared as my du, so it wouldn't work. So we would have to use CT. Okay. So, but when we use CT, we always want to have a claim, right? CT has two cases. We have the case where CT, like the series converges, and we have the case where it diverges, because we're looking for different things based on the case that we're in. So just based on rough intuition here, let's see if we can kind of isolate a approximation function. Like, can we see a function that kind of dominates here, that controls the series? And does that dominating function, does it converge or diverge? In this case, I'm particularly looking at 1 over n squared. N squared grows bigger than ln does, right? And a lot faster in particular. So I'm going to prioritize the n squared over the ln n, just in general. And does 1 over n squared converge or diverge? Yeah, it converges because it's a p series. P is equal to 2, which is greater than 1. Okay, awesome. So that's kind of my intuition just in my head that's rolling around that tells me that this is probably going to converge. So I'm going to make a claim. I always start with a claim. Claim that it converges. Okay, and let's see. Well, we know, so I'm going to skip a few of the things here that you need to check, but there's a few things that you need to check. You need to check positivity of both functions, and then you need to bound, right? So let's bound this function. This is our an. Sorry. So we're going to try and bound this from above, right? Because with convergence, you want to find a function that's bigger than it, that can kind of trap the sum. But what can we bound it above by? I like the 1 over 2 n squared. Why can we bound it above by 1 over 2 n squared? 1 over 3 n squared? Hmm. What do we know about ln? Over the positive numbers, what is always bigger than? Or, well, when n is greater than 3 in particular. What do we know about ln of 3? This is bigger than 1, right? Because notice this. These things are not put there for no reason. The details are always telling you what to do. So be very keen on this, the details. Ln of 3 is greater than 1. Okay, so let's work around this. So let's see. Uh, if we want to bound this from above, we need to we need to maximize the numerator and minimize the denominator. So does this tell you that ln of 3 or ln of n is always going to be greater than 1? It will be, because our n's will always start at 3. We need a lower bound of ln n because we're trying to minimize, or yeah, we're trying to minimize the denominator, right? So when you're bounding from above, this is maximize numerator or minimize denominator. So you're good, don't worry. Everyone's learning. Even me, I have to like double check in my head. I'm like thinking about, okay, if I make the numerator bigger, the thing is gonna become bigger. Take your time. So there's nothing in the numerator to really maximize. 1 is already really nice. So let's keep that. But let's minimize the denominator. The denominator is minimized by 1. So I'm going to call this my aside. And then this is just by aside, right? Make it really easy for yourself. If you have stuff written somewhere else, you can just call it something, move it over. So take this to be our function b of n. Notice that this converges by p equals 2, which is greater than 1. So by p series, which means that this also converges, but by CT. So remember with CT, you're using 2 series tests. You're not just using 1, you're using 2. You're using a CT to start, and then you're converting it to something that's easier to analyze. Okay? Make sense? Okay, and don't be concerned if you didn't get these. These are really hard. I chose some of the harder questions I could come up with. Don't be afraid if you couldn't solve these, because we're always learning. We're learning something now. Okay, to get to the integration. With the integration, again, it's very, very difficult because it was the previous stuff that we haven't seen in a while, right? Sure, we kind of touch on it with series, but it's mostly from the first part of the semester. But given that it's also part of the first part of the semester, the questions that she's going to give you is going to be harder. They're going to be really difficult because we can't just deal with baby integrals now. We have more tools. So again, with our integration, just to recap, we have u sub, int by parts, PFD, geometrically, don't forget that, properties, so our even and odd kind of functions, and then trig sub. Remember, trig subs always last. So for this one, oh, and we also have a CT. Sorry, did I not mention CT? I didn't mention CT. That's my bad. So I would probably put CT before geometric. CT. Okay. Well, I kind of mentioned CT. There's a reason I probably mentioned it, and it's because of this question. Is CT only for improper? CT is only for improper, yes. I had a general question about trig or arc trig type questions. Do we need to draw out a right angle triangle or does something like you like doing it algebraically instead of geometrically? So the thing is, as TAs, we don't know what the grading scheme is going to be beforehand. Surprisingly, so normally Kathleen, she actually gives a mark for, well, drawing the triangle, labeling the sides, things like that. And actually TAs prefer that because it shows your level of understanding. It also keeps you mentally in check just to make sure that you didn't mess anything up somewhere. I would suggest if you have like the 2 or 3 seconds, draw the little triangle. I honestly, I'm like you where I like seeing the algebra as well, but geometric will also, it'll help with your understanding of it. Yeah. So this was actually part of the last year's practice exam that was given. This question I feel like is just generally tricky. So this one's going to actually be a CT question. But remember, again, with CT, for integrals, for series, you have to have a claim. You need to claim whether it converges or diverges. So what do we think? Let me actually add that detail that CT is only for improper. What do we think? Do we think it converges or diverges? Okay. What tells you it converges? Okay, some people saying it's divergent. Okay, so this tells me that a lot of you didn't actually attempt or got stuck at this question on the practice exam, uh, and like left it, or they attempted it, but it didn't exactly work out how they planned. It kind of evens out to 3 square root x, which diverges. Yeah, again, remember when it comes to CT, we always try to look for the dominating terms. What are the things that will dominate our function? I'm particularly looking at this guy, 3 over root x. Notice that root x is the thing that dominates the denominator. It's the only thing that's controlling how big it gets. 3 in the numerator is what I chose because, well, cos of x is bounded above by 1. Arctan is bounded above and below by pi and negative pi over 2, right? Sorry, not pi and negative pi over 2. Positive and negative pi over 2. So those things multiplied won't get bigger than pi over 2, right? It'll at most be that. So the 3 in the numerator is the thing that's actually controlling it. And I like that. I like that idea. So let's take that to be our example to say that, yeah, it maybe diverges. Okay, but remember, when it comes to CT, you're always trying to define or you're trying to find a function that is positive that also guarantees or that also diverges. So f of x is equal to that. We also need to check if it's positive. Is it positive? You would have to show this explicitly, obviously, in full. But again, yes, quick check mentally, it's positive. This at the very least is going to be, sorry, probably shouldn't do that. This part at the very least is going to be negative pi over 2, which is less than 3. Or like the pi over 2 is less than 3. So minus pi over 2 will still make it positive. It's not going to deviate into the negatives. So we've done our little positive check. Now we need to bound it from below. So remember, when we're bounding from below, what are our options? What are we supposed to be doing? We're supposed to be maximizing the denominator and minimizing the numerator, right? So in this case, I'm actually going to do both. So notice that in our denominator, we have a very, very, very nice -1. We can just get rid of it. And again, do these steps separately because we want to see which option you're choosing for this step. So root x, this is maximizing the denominator. Justify it. What about the numerator? We already kind of said that the numerator, this part, this cos of x, arctan of x, that's bounded below, that entire thing is bounded below by -1 pi over, sorry, -1 times pi over 2, right? It can't get lower than that. So that means that we can minimize our numerator using that. Can we minimize it more? Can we make this function smaller? Or is it nice enough already? Yes, make it 1. We can't guarantee that it's going to be 1. We have to minimize it fully. 1 is still going to be bigger than this. Because remember what, actually, what it? 3.14 divided by 2. Okay, yeah, you could say it's 1. Sure. Yeah, that works. Okay, so this looks simple enough. Let's take this to be our g of x. Is g of x positive? Remember, with the divergent case, you have to check if g of x is still positive. With a convergent case, it's given to you by transitivity. Divergent case, you have to check it because you're making it smaller. This is in fact positive. Just a quick check can tell you that, right? On 8 to infinity, it's positive. Okay, and I will tell you that, well, I'm sure that you guys know how to evaluate this. Just take the integral of g of x. This is gonna diverge. You guys obviously need to show that it diverges by definition, but again, for the sake of time, I'm not gonna do that. So it diverges by definition, which means that the original integral diverges too by ct. Again, always, always, always tell me what series or integral test you're using. Can we ever say that does go does because it goes to infinity with the power series when um yeah, you can convert this to, so usually when we're using IT for series, we only ever go and take a series and turn it into an integral because integration should be relatively easier at this point in the course. But oftentimes it's actually useful intuition to take the integral and convert it to a series and use like a series test like the p-series test. So you can say that this diverges by, again, defining an to be whatever. That's still a lot of work, but it's possible. You can do that. And just say that p is less than p is equal to 1/2, which is less than 1, which makes it diverge. Because IT gives you an if and only if. But again, that's still a lot to show. So you're still kind of showing the same stuff, but just different amount of work. Okay, next question. Notice something here. Whenever I look at a definite integral, I always make sure to look at the bounds. Am I working over a symmetric interval? If yes, I have properties. If I'm looking at a symmetric interval, I have properties I can use and leverage. In this case, I'm going to determine if this is an even or odd function. Is my function in my integrand even or odd? If it's even, my life is still very difficult. If it's odd, though, it goes to 0. Beautiful. In this case, it's an extremely ugly integrand. No offense, but that's ugly. I have an absolute value there. I have a 1 over 1, or I have a 1 over x squared to the power of I don't want that. I don't want to integrate that. Chances are I can't even integrate that. But can I tell you what its signed area is? Probably. So all you have to do for this one is prove that it's even or odd. So remember your definition for even. Even is when its f of x is equal to f of negative x. Odd is when f of negative x is equal to negative f of x. In this case, it's going to be odd because we wouldn't make you integrate this. So it can't be your even case because if it's your even case, then it has to be something that's still integrable, right? By hand to find what it equals to. This one's going to be odd. So it's going to go to 0. So evaluates to 0. Just show this and you're good. Remember, you can't assume this. You have to compute each one individually. Compute what this is first, then this. You can't start by saying, oh, I have what both of them are on the left-hand, right-hand sides. I'm just going to see if they equal to the same thing at some point. Can't do that. You can't assume what you're trying to prove. But once you have this, you leverage a property and then you're good. Okay, this is my last integral question. Do you guys want to do this? Or should I leave it as an exercise? This is still a good question. But what would be the approach here? Yes. Yeah, that's x times tan squared x. So my general rule of thumb is whenever I see an x squared, or sorry, a trig function squared. I always think trig identities. Exactly, Alex. I think trig. So that means Pythagorean identities. So your tan squared is equal to secant squared minus 1, or your secant squared plus 1, in this case, would be equal to, sorry, tan squared plus 1 is equal to secant squared. You know what I mean? In this case, it's going to be the first one. So tan squared is equal to secant squared minus 1. You would distribute. So once that gets put in, you would distribute it. And then you would do an integ by parts. So an integration by parts afterwards. After distributing. Can you IBP at the start? Yes, technically you can. It's just gonna be more difficult. Who can tell me what the derivative of or integral of tan squared x is? Because whenever you have a polynomial part, when you're doing an int by parts, you want that to be the u, the thing that you're differentiating, right? So we have a polynomial part. This is always going to be u. Right? That's the thing that we want to disappear at the end. Does anyone know what the antiderivative of tan squared x is? I don't think so. I don't even know what it is. So, is that okay with everyone? Yeah. Tan x minus x? I'll take your word for it. I don't know what it is. But whenever you have a tan squared, always turn it into secant. Tan squared is not fun to have in an integrand. Okay. So there is about 13 minutes left. I don't think we're gonna get through all the questions. However, I'm willing to stay like back a little bit, right? So, but if you have somewhere to be at 3, by all means, you're allowed to leave. But let's crank through these. All right. I didn't think it would. I didn't think it would take this long. Okay, for your long answer questions, I really think that Kathleen will put a radius of convergence question on there, almost 100%. She loves these kinds of questions. They're very formulaic. They're very to the point. They have a correct answer, and they just check your knowledge on power series in general. In this case, this is a general power series. It's not a Taylor series. It's just a power series, and it's centered at 1. So with center, sorry, a equals 1, right? Because when you have an x minus a, this is your setup, right? Whenever you have a minus, it's going to be just what the number is. If you have a plus, it's going to be the minus of whatever the value is. So when it comes to finding the radius of convergence, it's always going to be a ratio test. And ratio test does this. It starts by defining what L is, your limit, in other words, as n goes to infinity, of the absolute value of an plus 1 over an. The order here matters quite a bit. You don't want to do an over an plus 1. It's always the more further along part than less. Just calculate it. Be very careful with your calculations. If you have something like this where it's a fraction and it's going to turn into a fraction over a fraction, always do it in the way that I show you. It keeps you like mathematically accountable and make sure your algebra doesn't mess up. So essentially for an plus 1, I'm going to just replace wherever I see an n, I'm going to replace it with n plus 1. So it's going to be, remember, our an part is just, it's just like our entire thing. So x minus 1 to the power of n plus 1 over n plus 1 times ln of n plus 1. Divided by. Notice how I'm putting no fractions over fractions. I don't like seeing fractions over fractions, and I'm sure that a lot of you don't either. This just makes sure I don't mess up anything. So again, same thing, but just keeping it normal. Simplifying, I'll get that this is like a keep switch flip kind of situation. So it's going to be an x minus 1 to the power of n plus 1 all over n plus 1 root ln of n plus 1. It's going to be multiplied instead, and I'm going to flip the denominator to be a numerator, ln of n, and then this is going to be an n, or x minus 1 to the power of n. Notice how I have a lot of things that cancel. I have this canceling with this, right? And then the rest of it is just going to be a limit that I'm going to have to take. So I'm going to get an x minus 1 on the outside. I'm going to use my properties of absolute values to split up the product. So now I have left a n times, or n over n plus 1 times, I'm going to merge these together. And remember, I'm keeping my absolute values. All these things have absolute values around them. Cool? So now what are we doing? I can move this outside because it's constant with respect to n. And make sure you justify that. All right, and now who can tell me what these things go to? So this guy, here's some really cool notation that I like to use. This guy goes to 1. This guy goes to this guy also goes to 1. Yeah. You can try that, or you can kind of intuitively think about that as, well, L'Hopital's rule kind of the inside, right? Like in your head, obviously, you can't take a derivative of a discrete valued function. However, you should use it as intuition. Ln of n's derivative is 1 over n. Ln of n over 1 or n plus 1's derivative is 1 over n plus 1. If you then take the derivative again of those and the quotient of them, you'll get a 1. So this goes to 1, this goes to 1. So each of these things go to 1. So this goes to 1. This goes to 1. That's kind of just like your showing of that. So we just have x minus 1. So what are we checking for this? We have 3 cases to check. Is this going to be greater than 0, or sorry, greater than 1, less than 1, or equal to 1, right? But in particular, we have convergence when this is less than 1. Right? It gives convergence when it's less than 1. So now we're just checking, well, solving for, well, what? What is our radius of convergence? Maybe it'll be more clear if I do this. Well, how far away can we be from our center? One. Yeah. This is going to be our radius of convergence. Really nice, really easy, really simple. So our radius of convergence is 1. You can also unravel this absolute value, right? To kind of check what your interval of convergence will look like. So unraveling, you would get -1 less than or equal to x minus 1 less than 1. This tells you that's going to be 0, x, and 2. So that means that x is within this interval, right? This is your radius of or this is your interval of convergence. Cool. So now, what if it also asks you to find whether this can, like, like the full interval of convergence, including whether it converges or diverges at the endpoints. When you're asked to compute an interval of convergence, it's not just this part. It's not just this. You also need to check the endpoints. So when for interval of convergence, you must check the endpoints. AKA, plug in the endpoints 0 and 2 as x in your series. Then you have to use a different series test to determine whether at those points it converges or diverges. If it converges, include it in your interval. If it diverges, exclude it. So as a little exercise, I would highly recommend find what convergence or divergence things happen at the endpoints. This is a little exercise because this is probably going to be something that's asked of you. Does that make sense to everyone? Yes, no, thumbs up in the chat if you understand. Ask a question if you feel like. Why shouldn't it be an if and only if condition? What do you mean? Oh, for this? So I don't like to write if and only ifs in math, just in general. When it comes to algebra, you can. Of course you can. But as first years, it's really hard to know when something is an if and only if. It's still correct to write the forward direction and only the forward direction because that's the part that we want. That's the part where we're interested in, right? So if we're putting a forward direction, we're just saying, hey, this is the part that we're interested in. Like we get this. This is the important part. Oh, for checking the endpoints? What do you mean? It's not like it's just like if you are asked to find the interval of convergence, uh you you have to check the endpoints. That's what I'm saying. I shouldn't have put like a double arrow there. But in this question, we only were asked for the radius of convergence, which means that we didn't need to find the interval, right? That's by default. The radius of convergence will always exclude the endpoints, which is why we have to check the endpoints. I'm going to tell you right now that at one of these endpoints, it's going to converge. At one of them, it's going to diverge. But you have to check that. If you're asked for the full interval of convergence, we'd only give you part marks if you don't include the checking of the endpoints. Yeah, if it's equal to 1, it's inconclusive. All right, I hope that answered that question. Um, this what if the limit does not exist? Well, then that means that uh the interval of convergence is everything. That means like R is infinity. It converges everywhere. Or actually, no, wait. Uh, if the limit doesn't exist, then that means it just diverges, right? If the limit is greater than 1, then it diverges. If it's less than 1, it converges. If it's equal to 1, it's inclusive. You can't tell. Basically, this is a way to measure the difference between uh subsequential terms as n goes to infinity. So difference so later terms. So if it goes to negative infinity, it would converge. Um, L has to still be greater than 1. So if it's equal to 1, we do another, yes, we do another test. L is always, because it's an absolute value, it's never gonna go to negative infinity, right? We're taking an absolute value of it, so it's never gonna equal to negative infinity. Does that make sense? If you got a negative limit, then you've done something wrong. If the limit is 0, is it the limit? I don't believe that it's possible to get a 0 as a limit here. But I think you just have to double check that. I think that that is true. Um, Let me actually think. Hold on. Yeah. That seems right. If the limit is 0, then the radius of convergence is infinity. Yeah, that does seem right. So if limit equals to 0, then that means that R is equal to infinity. So it'll converge everywhere. Yeah. Because then that just means that the distance between subsequential terms is going to be infinitely small. Like you can't even see them. And that just means that no matter what you do to it, it'll always go to 0. So that means that no matter what value you put in, it'll converge. Sorry, I didn't know that this question would like bring up so many side comments. But this is great. This is good. I like all these questions. Okay. Does that make sense to everyone? Does anyone have any other questions? Put a little thumbs up in the chat if it's okay. All good. Nice. Okay. Um, awesome. Okay. This question was on last year's practice final, or the practice final that you guys have access to. Um, or well, a similar type of question. But it seems like uh a lot of people struggled with this on the last year's final. So I thought I should definitely go over this. Or do you want me to skip this entirely? Go through it? Okay. I'll go through it. Yeah. I know that. Oh, skip. Oh. All right. So this kind of question, it originally was a prove or disprove. How many of you thought it was a disprove question because it was out of 5 marks? Just by like a raise of hand or like a thumbs up in the emoji thing. So if you thought it was a prove, put a thumbs up. If you thought it was a disprove, like I think a thumbs down is also an option. Okay. A lot of you are saying it's a thumbs up, like a prove question. Um, this isn't in fact going to be a proof because I mean the 5 marks as the allocated marks for this question is kind of deceiving. I think it should have been like out of 8 marks. But it is quite a simple and nice proof. It's not something that's like completely inconceivable. It's a few steps. All right. So proof. As always, when I'm listing or doing a proof, I always list out all the things I have access to. And I'll actually do this, yeah, in blue is fine. So let Bn, or sorry, An in this case, be greater than or equal to 0 because we know that it's a sequence of positive integers. So that means that all of these values are going to be greater than or equal to 0. I like seeing it in the mathematical form because it tells me what to do with them. All right. We also know it's a decreasing sequence. So let An be decreasing. I like the shorthand. It's really quick to write. Okay. So now, what does each of these things give me? Let's start with the decreasing. I feel like decreasing is always the thing that's kind of um like at the forefront of things. Decreasing gives me this relationship. An plus 1 is always going to be less than or equal to an. No, we don't have strictly decreasing. We just have decreasing. Okay. But this also tells me about, well, we're dealing with this kind of stuff, right? A of 2n minus 1 and 2n. Can we agree that 2n minus 1 is less than 2n? So that means that if it's decreasing, we'll have this relationship. Does that make sense? We'll have that the earlier term is bigger, right? Because it's an earlier term, right? Cool? And this is going to be a later term. So we have this relationship. So that means that we have that um a of 2n minus 1 minus a of 2n is always positive. Cool? It's always just something to note. It's something nice to look out for. Okay? But doesn't this kind of look like it telescopes? It's like a something minus a previous term or a later term. This kind of telescopes. It looks like it telescopes. So I'm going to actually consider the definition. The limit of Sn, which equals to the limit of the nth partial sum, which is a1 minus a2 plus a2 minus a3 plus a3 minus a4, and it keeps going, right? All the way until a of 2n minus 2 minus 2n minus 1 plus a of 2n minus 1 and then minus a of 2n. I know it's kind of confusing to write out this kind of pattern, but you should always really, really think this through. Think of it slowly. Okay, I'm taking the previous term and I'm subtracting the next term. Taking the previous term, subtracting the next term. Cool, so they're in like these kind of groupings, term-wise. Okay, but now, take a look. This indeed does telescope. Well, I have a negative version of this term and a positive version of the term. Negative version of the term, positive version, negative version, positive version. You should always write at least 2 to 3 of these cancellations out fully, just to convince the reader that you've actually checked that it does in fact telescope. Okay, something in here is going to cancel out with something in here. I'm confident of that. Something in here is going to cancel out with something in here. Amazing. So what does this full thing simplify to? Well, it simplifies to the limit of n approaches to infinity of a1 is the only term that didn't get canceled out from the very beginning, and a of 2n is the thing that canceled out at the very beginning or at the very end. Everyone see how this telescopes? So by telescopic pattern or behavior. Okay, and we're actually almost done. How do we know that? So now we just need to determine, does this exist? Does this limit exist? And what do you guys think? Does it exist or does it not exist? No, not quite. So remember, we're always taking the previous term, or yeah, we're always taking the previous term and subtracting the next one. So let's generate it term by term. When n equals 1, what happens? When n equals 1, it's 2 minus 1, so it's the first term. So a of 2 times 1 is 2. Okay, next term, n equals 2. 2 times 2 is 4 minus, wait, hold on. Oh, okay. Yeah, you're right. Even I wasn't careful. But this would still be 2. Mm, sorry, let me rewrite this down. That changes things just a bit, but yeah, it really doesn't change much. So an minus that plus a3 minus a4 plus what would be next? It would be a5 minus a4. Keep going. Minus a2n minus, sorry, this should be a 3 minus 2n minus 1 and plus a of 2n minus 1. Oh, is it a5 minus a6? It is 2n. Okay, yeah, so it would only be the even numbers. Those would be the other numbers. Okay. As n equals 3, this would in fact be 5. Okay. So we can section them off into the even and odd parts of it, right? So the limit as n approaches to infinity of the odd parts, so a1 plus a3 plus all the way to like a of 2n minus 1, right? And then we have a of, or a2 plus a4 plus all these parts, a of 2n. The first 2n minus 1 should be 2n minus 2. Yes, you're right. Thank you. Okay, did I index those all correctly? I'm guessing I did. Um, so what do we know about these? Let's section them off. This is just s of 2n minus 1, s of 2n. This is just going to use a very simple thing. So we know that all these parts, this is a finite number, this is a finite number, right? All these things are finite numbers. We just need to make sure that these things at the ends, those don't blow up to infinity. But we know that they don't. Don't we subtract them? Oh yeah, sorry. Doesn't really change the proof, but yep. Thank you. I'm going to argue that we know that they don't. They don't blow up to infinity. We know that their limit exists and we know exactly what their limit is. But how do we know? Well, let's take a look at what the information we have is. Well, we have that sequence is decreasing, and we have that it's bounded. And particularly, we have that it's bounded below. Right? So by BMCT, remember, these are sequences. BMCT tells us that the limit is finite. And we know that both of their limits have to be the same thing, right? So I'm gonna call it L. So let's call it L, because why not? Okay, great. So that means that we know what the limit of this guy looks like, and we know what the limit of this guy is. We know that it's just equal to L. But all these things are just numbers, right? And they're all constant with respect to n, other than those guys, right? Just by our limit laws, we can distribute limits over constants. So that means that we have A1 plus A3 plus all the way up until whatever. And then we have our limit of A of 2n minus 1. And then we have the subtraction of the same thing. We have the A2 plus A4 plus all the way up until we subtract the limit of A sub 2n. But we know what both of those things equal to. This goes to 0. This goes to 0. Right? Just by BMCT, we know that their limit will tend to 0 because of their bounded behavior. So by BMCT. Does that make sense? And then all the rest of these things are just constants. Adding and subtracting constants won't blow up to infinity or negative infinity. Which means that this converges. And in fact, it'll absolutely converge because we proved that the interior, so if we took the absolute value of these things, we proved that the interior was greater than 0, right? So if it converges, it absolutely converges. And I think that's what the original question was, but I just changed it to converges because it was less confusing. Should it be its largest bound instead of 0? Well, actually, when we're so yes, technically, but even then, it would just go to whatever that L is, right? So sure, let's call it L, just for clarity's sake. But yes, it should be its largest bound, largest lower bound. So it's infimum. Is that good with everyone? Sorry, I originally thought it was telescopic for some reason. I just wasn't careful with writing it down. Okay, I know. Really complicated. Not worth it for 5 marks. But the reason that I think Kathleen put it as 5 marks is because of how complicated it actually turned out to be. So she didn't want it to make like a huge loss if you didn't get it. But if you did get it, great. You have a chance at 100%. Okay, put like a little thumbs up or a little indicator saying you got it or you didn't, if possible. Okay, but I did have one last question. So would this be like an extension question? Because Kathleen says she likes to put an extension question on them. Yes. This would be a very extension question. And it's usually like these extension questions are based or they're graded a little bit more leniently. So if you put things down that actually get you closer to the final answer, even if they have like very wishy-washy justification, it'll still get you marks. I think this was the extension quote unquote question that Kathleen put last year, and very few students got it. Like I think it was like 1 or 2, and those 2 ended up being TAs. Okay, but very last question. Provide a series such that AN diverges, but the subtraction of the 2 converges, like the subsequential terms. What can we put as this? Well, let's think of our quintessential list of, or our canonical list of divergent series. Divergent series usually look like this. Well, our classic example is the harmonic. Do we think that something like this will converge? Yeah, this is just telescopic, and it'll converge. But you just have to prove it because I said prove. Okay, that was a lot. That was a lot to take in. Exactly, yeah. Intuitively, 1 over n barely diverges, right? It's so close to being convergent. But yeah, so if you're taking the difference of the things, you're basically just getting rid of the parts that make it diverge. Okay, we covered a lot today, and we didn't go over any definitions or anything. Well, we kind of did, but kind of didn't. Were there any questions overarchingly that you feel like you had, but you didn't get answered, that I can maybe answer right now? There is about like, well, we're over time by like what, 30 minutes, but I don't really mind. Um, do you guys have any questions from 3 from the series? Could we consider the even and odd cases of n so the limit does not equal to 0 for both? Yes, that would be a good way to show that the limit doesn't equal to 0. Right? Because if we know that a limit exists, then that means that the limits for both or all cases need to be the same. If they're not the same, then the limit doesn't exist. Yeah, you can screenshot the checklist. Yeah, here we go. Is it possible to use L'Hopital's rule for this as well? Yes, you could use it implicitly like a L'Hopital's rule, but don't actually call it L'Hopital's rule. Um, but you could say intuition and then say like L'Hopital's rule, this kind of function does this with L'Hopital's rule, and then it kind of tells you what to do with the discrete function. The thing is that we just can't formally apply L'Hopital's rule to a discrete type function. For the radius of convergence, if the limit is 1, what would you recommend us doing? Okay, if the limit is 1, then I recommend a GS because that also involves powers. Um, but it's very rare that ratio test will fail for these kinds of things. So I would recommend GS or probably div test. I probably wouldn't suggest using P series. And CT would also work. Um, so it's not that it doesn't work, Dion. It's the fact that I didn't consider that when creating the question, so that's actually my bad. I probably should have said something like it doesn't equal to 0. Um, or it's greater than or equal to 0 for all x on, sorry, probably should have said greater than. Uh, actually, and continuous. That would probably be it to make this false. Okay, now that I see, I probably should have thought better about this question. Uh, why the second last question will not be blown up? Um, let's see. The second last question was this one. Um, it's because of BMCT. BMCT guarantees that if you take the limit of any of our sequence elements, it'll go to a number. It's not gonna go to an infinity or a negative infinity. It doesn't diverge because this is the case of BMCT where decreasing bounded below. And because it's decreasing bounded below, we have BMCT tells us that it converges, which means that by definition of convergence, we have that it has a limit. Convergent sequences. Yes, I can show the pages at the top. Is there any specific question that you want to like stop over or off topic? For Calc 3, do we need do we need these 8 tests? Um, I remember Calc 3 being very much like you won't need to use CT. You'll need to use integration by parts and a U sub. That's pretty much it. You'll never really need to use anything else. Um, yeah, especially since Calc 3 is more like computation based and it's mostly for physics students. Unfortunately, it's not gonna involve something like super complicated. Could you please show first part A to I? Yes. So here's part A, part B, part C. Okay. Um, we're all about 30 minutes overtime. To those of you who stuck around, thank you so much for attending the review seminar. I really appreciate it. To those of you who uh, you know, had your finals or this is your last final, good luck on your very last one. I wish you the best of luck. Um, as a reminder, I do have past review seminars also posted on YouTube if you can find them just by Google searching. You can search up MATA37 review seminar or final exam review seminar. It's going to be the one that's from a YouTube account under my name. It's not going to be the AMAX one, although the AMAX ones are very useful. Just note that the summer semester one is not going to have the same content coverage, so it's going to be a little bit different. But just extrapolate the information. Yes, it's under that username. Um, and what was I going to say? Oh, I also have office hours on Monday, I believe. It's probably one of the earlier office hours, but still kind of midday. So feel free to pop by the math help room if you need help. If you need me to explain something a little bit more in detail, if there was something that from today that you didn't really understand, or if you just want to chat and just say hi. So with all that being said, thank you so much for attending the review seminar. I really hope you guys do well. I'll see you at the final. Thank you guys so much. Bye, everyone.